Hi everyone, I am SS Kiran. I would like to discuss about some standard signals or basic signals in signals and systems. Okay, now in this video I will cover, these are all topics like DC signal, sinusoidal signals, unit step signal, Signum function, rectangular pulse, delta or unit impulse function, unit ramp signal, continuous, time, complex, exponential. Okay, previous video I have discussed introduction about signals and systems, definition of signal and system, a classification of signals, and some comparison between energy and power signals. Okay, now we will enter into the basic signals. Okay, see here, these are all called some standard signals. Okay, now in signals and systems some of these standard signals are used. Okay, these standard signals are represented graphically and expressed mathematically, so that you people concentrate on every signals graphical representation and mathematical representation with condition. Okay, that is very important. These are all signals are compulsory, we can represent in a graphical form and mathematical representation. Okay, some of these standard signals we are discussing now. Okay, again I will read: DC signal, sinusoidal signals, unit step signals, Signum function, very important, rectangular pulse, delta or unit impulse function. Then seventh one, unit ramp signal. Eighth one, continuous, time, complex, exponential signals. Ninth one, Sinc function. Last concept, very important concept, relation between step and ramp and delta. This relationship very important. Okay, now we will start with DC signal. Okay, all signals here classified and discussed with two types. One is continuous time DC signal, discrete time DC signal. Okay, let us take DC signal. A signal having constant value with independent of time is called a DC signals. Sometimes there is a chance to ask definition of DC signal. You have to write this definition. A signal having constant value with independent of time is called DC signal. We will see the graphical representation and mathematical expression. Okay, this is the graphical representation. You can see here there is an amplitude A, one DC signal minus infinity to infinity. See here, minus infinity to infinity. These type of signals maintain constant amplitude. These type of signals is called DC signals. A continuous time DC signal is graphically represented as shown here. See here, as shown here. Okay, it is mathematically represented as the time period is A, or voltage or current, whatever it is, time period is equal to A for condition equal to minus infinity to less than t less than infinity. See here, this is minus infinity, this is plus infinity. The signal is between minus infinity to plus infinity. So function is x of t equal to A for condition is minus infinity to less than t less than infinity. Okay, here where A is the amplitude of the signal. I think you must very much clear about this one. A is nothing but the amplitude here. Okay, this is the DC signal for continuous signal. Okay, actually we can classify it into two types. One is continuous time, another one is discrete time. I mean, I have given clear explanation in previous video. What is the continuous time signal? What is the discrete time signal? Just you go through it. I have provided link in my description with the notes. You can understand, right? Now, a discrete time DC signal is graphically represented as shown here. Very simple. We can represent it in a discrete model. See here, you can understand different time intervals here. Okay, this is the constant DC signal in discrete time. Okay, discrete time signal, right? Same, but coming to expression in equation, we can denote x of 1 because of discrete time signal. Coming to analog, we can take x of t for continuous time, x of n for discrete time. Okay, x of n equal to a, same condition is maintained, same, minus infinity less than n less than infinity. Okay, it can also be expressed in the infinite sequence. Yes, absolutely. See here, so and so, a comma a comma a comma, so and so, because of minus infinity to plus infinity, we can also express like this also. Okay, the first standard signal, basic signal is completed, right? Now the second standard signal is sinusoidal signal. Before going to the definition, see here, graphical representation. It can be looks like a sine waveform. Okay, this sine waveform is nothing but sinusoidal signal. Okay, this is cos waveform. See the variance. Okay, start with maximum value here. Okay, half of the peak, right? This is the sinusoidal waveform. This is the cosine waveform or cos waveform. Okay, now the second standard signal is sinusoidal signal. It includes sine and cosine signals. Absolutely right. Now we will start with continuous time signals. Okay, continuous time signals is shown in following figure. Just now we observed here. Okay, then mathematically represented as very simple. This is a sinusoidal signal. Simply you can write sine t. It's having some time period. You can mention sine omega t with amplitude a. Then we can write on mathematical form or mathematical expression x of t equal to a sine omega t. Omega is an angular frequency. We can also call omega equal to 2 pi f t. So we can write x of t equal to a sine omega t. Again it is converted into a sine 2 pi f t. Okay, now continuous time cosine signal is also same. Cosine signal is represented with cos having some amplitude. Now equation is x of t is equal to a cos omega t. Again omega we can write 2 pi f. Now it is changed into a cos 2 pi f t. Okay, this is the continuous representation. Now we will see discrete representation. I think you know how we can represent as a discrete, right? This is the discrete representation. In y-axis you can take x of n is same. Okay, in x-axis we can represent some integer number that is called n. Okay, this is the sine wave in the discrete time signal. This is the cosine wave in the discrete time signal. Okay, how we can write the mathematical equations? Very simple. So we can start with x of n equal to a sine omega n. Just you have to verify here. Here we can write n because of this is the discrete time signal. A sine omega n. Omega is a angular frequency. Omega we can write as a 2 pi f. Okay, same equation. Same is in the cos. X of n equal to a cos omega n. Again we can represent a cos 2 pi fn. Same phenomena, right? Our next, the first signal DC signal is completed. The second signal sinusoidal signal is completed. Now we will enter into the unit step signal. Step signal, by using step signal we can solve many problems. Step signal is represented with u of t. u of t is nothing but unit step signal. Okay, u of t equal to 1, you have to write one condition for t greater than 0. Very important, u of t equal to 1 for t greater than 0. For every standard signal you have to concentrate this graphical representation. At the same time you have to concentrate on this conditions also, mathematical representation with condition. Okay, now we will see the definition. First, both this is also classified into two categories. We can describe in two categories. One is continuous time unit step signal, another one is discrete time unit step signal. Okay, now we will start with the continuous time unit step signal. Okay, has a constant amplitude to unity for an 0 or positive value for the time t. See here, the positive value, this in x-axis we can represent a t at 0 to some positive value, we get some value is answer 1. So that is called u of t equal to 1. So as per the graphical representation, we have to write the definition. Continuous time unit step signal has a constant amplitude of unity, that is equal to 1 for the 0 or positive value. Then t has a 0 value for 0. One is one unity for a positive value, 0 for negative value. See here, we can represent mathematical form. U of t equal to 1 for t greater than or equal to 0. Again, u of t equal to 0 for t less than 0. This is the mathematical expression for unit step signal of continuous time. Okay, now discrete time. So discrete time, which parameter is changed? This n integer parameter is changed. Now how we can write? Discrete time unit step signal is denoted by, very good, u of n. Its value is same, unity for all positive values of n and 0. Yes, same definition for negative value of 0. Same condition, just only change the parameter, that is called n. Okay, same, we can in x-axis you can take n, in y-axis you can take x of n. So what about expression? See here, u of n equal to, here x of n, u of n equal to 1 for n greater than or equal to 0. Now u of n equal to 0 for n less than 0. This is the mathematical representation for discrete time unit step signal. Okay, now we will enter into the fourth standard signal, that is called Signum Function. What it is called? Signum Function. Very important function. It is defined as for both continuous time signals and discrete time Signum Function. Continuous time Signum Function and discrete time Signum Function. Okay, first you can concentrate graphical representation. I have told many times, for every signal you have to concentrate graphical representation and mathematical representation. Okay, this is the graphical representation for continuous time Signum Function. Okay, see here. Okay, now how we can write the mathematical equation? So Signum Function can be denoted by sign of t or sgn of t. Sign of t, this is called signum. Sign of t equal to 1 for, see here, t greater than equal to 0 for one condition, t greater than equal to 0. For another condition, -1, t less than or equal to 0. Not less than, just simply I can write less than, not less than or equal to. So what is the mathematical expression here? Once again see, very important. Sign of t equal to 1 for t greater than 0. Sign of t equal to -1 for t less than 0. This is the condition for, this is the mathematical expression for continuous time Signum Function. Okay. continuous time Signum function. Now we will enter into the a discrete time Signum function is obtained same, but you have to change in y-axis x of n equal to sign of n. In x-axis we can take n. Okay, now we can represent in the mathematical form. So very simple. In the previous continuous signal you have to take sign of t. In this signal you have to take sign of n equal to 1 for n greater than 0, minus 1 for n less than 0. Okay, this is the mathematical representation. Now we will enter into the another standard or basic signal, that is called rectangular pulse. This is called rectangular pulse. Okay, some time period minus 1/2 to 1/2. How we get the form? See here, very simple. Just by observing the this graphical representation, you can write the definition also. A rectangular pulse of unit amplitude and duration is shown. Okay, see here how we can represent this rectangular pulse. Rect of t, R-E-C-T, rect, this is called rect of t, equal to 1. What is the mathematical expression condition? Minus 1/2 less than or equal to t greater than or equal to plus 1/2. Very important condition. See here, this only this part we can show only one. That's why how we can write t less than or equal to minus 1/2 less than or equal to t greater than or equal to plus 1/2. This is the mathematical expression. Remaining all parts like otherwise it can be treated as a 0. This is the rectangular pulse. Let us, we can take one example. If time period is t, amplitude is a. So how it will be convert? So amplitude a minus t/2 plus t/2. So how it will be changed? Rect of t by capital T equal to a for minus t/2 less than or equal to t greater than or equal to t/2. In any condition it can be treated as a 0. Okay, same phenomena we can also describe in the discrete time rectangular pulse. Okay, how we can add this expression? Same mathematical expression. I only concentrate on how to write mathematical expression. This is the graphical representation. See here, you can understand. Now we will enter into the mathematical expression. So here n can be taken as a frequency fm. Nothing to worry. See here, mathematical expression. X of t equal to rectangular of n, rect of n equal to 1 minus 1/2 less than or equal to n greater than or equal to 1/2. Other condition, otherwise it can be treated as a 0. So this is the rectangular pulse. Okay. Now another standard signal is delta or unit impulse function. Okay, this is the another standard or basic signal, that is called delta or unit impulse function. So this unit impulse function is also called delta function. That's why in function we can identify with delta of t. Okay, this is the continuous. This is also can be treated as two categories. One is continuous time signal, another one is discrete time signal. What is the mathematical expression? See here, you can understand. This is the first one. This is the mathematical expression. X of t equal to delta of t equal to 1 for t equal to 0. Other condition, t not equal to 0, at any condition delta of t equal to 0. Delta or unit impulse function. Okay, so mathematical expression minus infinity to infinity delta of t equal to 1. Okay, if you want to write the definition, see here, one of the simplest discrete time signal in the unit impulse function. It is present only n equal to 0 or t equal to 0. By graph itself you can understand. Okay, t equal to 0 and n equal to 0, we get only value equal to 1. Okay, its width is 0 and its amplitude is infinitely large at t equal to 0. Okay, this is the expression for delta or impulse function. Okay, see mathematical expressions here. X of t equal to delta of t equal to 1 for t equal to 0, for t not equal to 0, for 0 for t not equal to, same expression. X of n equal to delta of n equal to 1 for n equal to 0, 0 for n not equal to 0. It can be represented in the discrete time unit step. This is represented continuous time unit impulse. Now next, unit ramp signal. Okay, the signal which increases linearly, see here, the signal which is increases linearly, this signal we can call it as a ramp signal. Okay, ramp signal is nothing but which is increases linearly with the time is called unit ramp signal. So sometimes there is a chance to ask define the ramp signal. Simply you have to write this definition: the signal which increases linearly with the time is called unit ramp signal. It is denoted with ramp signal is denoted with r of t. Okay, just you have to concentrate mathematical expression, very important. Every mathematical expression with condition and graphical representation. This is the graphical representation. Okay, this is the mathematical representation. R of t is equal to a t for t greater than or equal to 0, r of t equal to 0 for t less than 0. Here a can be treated as a slope. This is the ramp signal. Okay, just this is the ramp signal for continuous time unit ramp. Thus you can observe ramp signal, continuous time unit ramp signal. This is the this is the discrete time unit ramp signal. So in x-axis you can take n integer, in y-axis you can take x of n equal to rn. Okay, r of n. Okay, now how we can write mathematics? Very simple. R of n equal to an for t greater than or equal to 0, for 0 for t less than 0. A is called the slope. Now, very important topic, that is called complex symmetrical or complex exponential signals. Okay, these complex exponential signal can be classified into two categories. One is real exponential signals and periodic complex exponential signal. Okay, just these signals, which type of signals? E to the power of minus alpha t. These type of signals we can call it as a exponential signals. Of course, e to the power of alpha t or e to the power of minus alpha t, e to the power of minus at, those signals is nothing but the exponential signal. How we can be defined by the real or periodic complex exponential? See here. See here c and alpha are general complex numbers. So our given expression equal to x of t equal to c into e to the power of alpha t. Okay, can you observe here there is a two graphical representations. One is decreasing exponential function. Simply you can write x of t equal to e to the power of minus alpha t. Very simple. If it is decreasing exponential function, that can be treated as a e to the power of minus alpha t. For example, if it is raising exponential, you have to draw like this. Okay, x of t is equal to e to the power of alpha t. So nothing to worry, just concentrate on diagrams, you can understand. Okay, see, I mean in my description I have provided, just you go through it, right? What about periodic complex exponential signals? In periodic complex exponential signals, alpha purely imaginary. Here alpha is real. Okay, in real exponential, alpha is real. In periodic complex exponential signals, alpha is purely imaginary. Very simple. If alpha is imaginary, then x of t is converted into a e to the power of j omega naught t. Okay, so omega j, this j is an imaginary part. Okay, same representation, x of t equal to e power of j omega naught t. T can be write as a t plus t, t plus capital T. Okay, finally we can write the above relation, e power of j omega naught t equal to 1. See here, you can understand, nothing to worry. The final one, discrete time exponential, we can also both represent in the discrete and continuous. This is the exponentially delaying function for discrete time exponential signal. This is graphically represented exponentially raising function. Just simply you concentrate e to the power of minus alpha t. Okay, alpha t is a decreasing exponential. If it is increasing, simply e to the power of alpha t. This is the two basic signals. Okay, Sinc function, the last standard signal, very important signal, the graphical representation of the Sinc function. See here, this is the Sinc. So this also sometimes also comb function also we can call it sometimes. Okay, Sinc function, the mathematical representation is nothing but Sinc of x is equal to Sinc pi x by pi x, whatever we have within the brackets. Okay, that degrees term, that same we can represent in the some numerator by denominator is same. Okay, so Sinc pi x by pi x for condition equal to x equal to 0. So this is the Sinc function for graphical representation. See here, this is the Sinc function. The mathematical expression is Sinc of x equal to sin pi x by pi x. Okay, for x equal to 0. Okay, this is Sinc function or Sinc pulse in mathematically expressed as the following equation. Okay, see here Sinc function. Okay, goes on decreasing as the value of mod x decreases. See here, you can understand, just read the definition, right? The next topic is relation between step, ramp and impulse function. A very important relation. U of t equal to differentiation of r of t. R of t is nothing but the ramp signal. U of t is nothing but the unit step signal. How we can define? U of t equal to differentiation or d by dt of r of t. What about r of t? R of t is in the terms of u of t, very simple, r of t equal to integral u of t into dt. Okay, the one more relation that is called relation between step and impulse. Impulse can be also called as a delta function. So that's why we can denote it with delta of t equal to d by dt into u of t. Okay, what about u of t in the terms of impulse function? U of t equal to integral delta of t into dt. These two relations are very important. Once again, see here, you can understand, right? Okay, the next one. So I will quickly revise all with only mathematical form and graphical form. See, first the impulse, delta of t equal to 1, t equal to 0, t not equal to 0 for 0. See, only some quick reference. Okay, this is the mathematical expression. See next one, unit step. U of t equal to 1, t less than or equal to 0, t greater than or equal to 0, for 0, t less than 0. See quickly, you can understand all the functions. Signum of t1, 0, minus 1. See here, ramp r of t equal to t for t greater than or equal to 0, t less than or equal to 0 for r of t equal to 0. See graphical representation. This is the impulse train. See here, for in the discrete form, this is the rectangular signal. See the condition. Okay, already have discussed every signal, triangular signal and Sinc signal. Okay, this is the triangular signal and this is the Sinc signal. Just you have to check and basic signals. These are all the basic signals and standard signals. Okay, thank you so much. Thank you. Next video I will discuss some transformations, right? Thank you so much.